let's talk about buffers. So at this point, we have talked about acids individually, bases individually, that's chapter 13. Then we talked about acids and bases together, that's titrations. And now we're going to talk about buffers, which is also about acids and bases together. So buffers in their simplest form are made up of a weak acid or base and its conjugate. So we're talking about if it has a weak acid, it's going to have its conjugate base, or if it's a weak base, it's going to have its conjugate acid. So let's just think about that. Buffer, as you may know, what a buffer is it's a solution that resists a change in pH. So normally, if we add an acid to, say, water, the pH changes dramatically, or if we add a base to water, the pH changes dramatically. But if you add it to a buffer solution, one that has both a weak acid or a base and its conjugate, its pH doesn't change dramatically. So let's say, for example, we have acetic acid, that's a weak acid, and its conjugate. So in this water solution, we have both the acetate ion and acetic acid. That would be a buffer because, and here's why it's able to resist a change in pH. If I were to add an acid, so something that contributes H+ ions, the acid that I add is going to react with the basic part of the buffer. And that's an acid-base reaction, and it's going to form acetic acid. Now, acetic acid, of course, undergoes an equilibria, but it mostly sticks together. So what it does is this is sort of acting like a sponge to get rid of the extra H+ that would have changed the pH. If I were to add a base, something that's providing OH-, it's going to react with the acidic part of the buffer. So if I add OH-, which would directly change the pH, because OH- times H+ is Kw, it's going to react with the HAC, and that's going to produce water, and the AC-. So again, this is going to act to tie up the OH-, so it's not present very much to change the pH. Same thing, this is basic, and so, the pH may change a smidge, but nowhere near as much as if I had the H+ or OH- directly. Now, of course, that does lead to something known as buffer capacity, because I could add a small amount of acid or base, and as long as, there's something in there to react, the pH won't change much. But there's only a limited amount of the acid or the base. So if I, for example, continue to add H+, the AC- will react with it until the AC- is all gone. And then you've reached the buffer capacity. It's run out of the buffering substance, I guess, so to speak. So as we keep looking at this, I want to tie that into the titrations that we've been doing. So in our titrations, let's say, we were titrating, we have NaOH in our burette, and on our Erlenmeyer flask, we have some acetic acid. We've done a bunch of math with this. And we've also drawn our titration curve of pH versus, milliliters of NaOH added. And, we had this curve that looked like this. Woo, it's kind of bad. Let's make it prettier. But something that looks like this. And so one of the things that we kept looking at is, what governs the pH? What's impacting the pH? What's most important? And we had said, okay, you know what? At this point, at 0 milliliters of base added, the only thing that's in there is the acetic acid, and that's what's going to influence the pH. And then over here at the equivalence point, because, we're reacting acetic acid, I'm going to do the net ionic here, plus the OH-, we're getting water and the acetate ion. So at the equivalence point, these things are gone, which means it's the acetate ion that's governing the pH. And then Up here in this region where we have lots of extra OH minus, it's the OH minus that's governing the pH. But along the way, right in here, so anywhere above 0 but not to the equivalence point, this is a region where this is the take that back, hang on. The OH minus is the limiting reactant, which means we run out of OH minus first, which means anywhere in the green area there is leftover acetic acid and the acetate ion has been produced. So anywhere in this region there are two things affecting the pH, governing the pH, acetic acid and the acetate ion both. A weak acid and its conjugate base. Oh, look. It must be a buffer. That literally means that what is in this flask, above 0 but not yet to the equivalence point, what remains in the flask must be a buffer solution because it actually has both a weak acid still left in there and the conjugate base, both. Okay. So, why is that important? Okay, first of all, buffers have a lot of important aspects to them, and so we're going to talk about in class, you know, where buffers are important. For example, your body would be an important place. Buffers are important in trying to come up with a pH or a lack of a pH change. But let's talk about some mathematics of buffers and perhaps a shortcut. So let's say we have some weak acid, HA, and it breaks apart into H plus and A minus, and we know the Ka is going to be, we've done this a million times, H plus times A minus over HA. And then I'm going to rearrange it, and this time I'm going to rearrange it to solve for H plus. So if I do that, H plus becomes equal to the Ka times HA over A minus. And now I'm going to negative log both sides. I'm trying to get to a shortcut. So if I do that, negative log of H plus is equal to negative log of Ka plus the negative log of HA over A minus. And I'm doing this kind of specifically to make a point. And of course, we know that the negative log of H plus is pH is equal to the negative log of Ka, that's the pKa. And now, instead of doing a negative, I'm going to reverse these, plus the log of A minus over HA. This equation is known as the Henderson-Hasselbach equation. A, that's H, oops. Now, the AP test will never ask you about the Henderson-Hasselbach equation, but the reality is it's a nice shortcut, and there's nothing wrong with the science. So it certainly could play a role here as long as you understand what it could be used for. So I'm going to show you one example of what it could be used for to simplify our lives. And so here's a question. What is the pH when 49.9 milliliters of 1 molar sodium hydroxide is added to 50 milliliters of 1 molar HAC, and the Ka is 1.8 times 10 to the minus 5. We did this problem already. We did it when we did the titrations, and we are going to do it the short way now instead of the long way, so we can see how the Henderson-Hasselbach equation can help us to simplify some things. So here we go. As we did before, we're going to write the neutralization equation. So acetic acid plus, I'm going to ignore the spectator sodium ion, gives me water, and the acetate ion minus. And as you recall, we would do a moles ice table to figure out what was left so we could figure out the equilibrium. We're going to do the same thing. We're just repeating this. We've done this before. So we had 0.05000, and then if we find the moles of this, it was 0.04990. Water we don't care about, and we didn't start with any acetate ion. This is acid plus base, so this goes to completion. You can see right now we're going to run out of OH minus. So we're going to lose this. And we're left with 0.00010. And we'll gain it over here. It's a 1 to 1 to 1 to 1 ratio. That might have been too many ones, I don't know. Awesome. Now, at this point, what we did before was we said, oh, okay, look, we've got acetate ion, we've got acetic acid. We're going to go ahead and we're going to do the equilibrium, use the, do a new ice table with molarity. We're going to use the Ka and all that stuff that we did before. But we're going to shortcut it today. So we're going to acknowledge right now that we currently have a weak acid and its conjugate base in both. What that means is at the end of this reaction, we have a buffer solution. So we can use the Henderson-Hasselbach. pH is equal to pKa plus log of A minus over HA. Okay. We're trying to find the pH. So the pH is equal to the negative log, I gave you the Ka, 1.8 times 10 to the minus 5, plus log of A minus. Okay, A minus. This is moles. So for A minus, it's 0.04990 moles. And I had 50 plus 49.9 milliliters, so 0.09990 liters. That is my concentration of AC minus, or A minus in the equation. My acetic acid, I have 0.00010 moles over the same volume. That's my acetic acid concentration. Now you guys here, let's shortcut it again. The number of moles came from my ice table up here. But notice they're naturally going to be in the same volume because they're poured together. So these volumes cancel out. So what I could do instead is, pH is negative log of 1.8 times 10 to the minus 5 plus, and just do a log of the moles only. So the number of moles of AC minus is 0.04990 moles over the 0.00010 moles of my acetic acid, and I don't even need to put the volume in because it canceled. And it will always cancel because you poured them together. They're in the same volume. And now this is easy. You plug it into your calculator, the negative log of this plus the log of this, and you find the pH is equal to 7.44, which is the same answer we got by doing all the equilibrium and the Ka and all that stuff that we did before. But now we can get it a little quicker and easier. The key here is being able to know that after I do the ice table, I had some weak acid and its conjugate base. As long as those two are present, then I can use the Henderson-Hasselbach in order to calculate that. Okay, the rest we're going to do in class, so we'll see you later.